Join us as we explain how to use the LabRadar Doppler chronograph for determining the coefficient of drag and ballistic coefficients. First, explain what we're doing and why, then focusing in on the technologies involved, in particular the LabRadar. Explain how to reduce environmental data, then move on to data from the LabRadar, briefly discuss Mach regimes, standard drag models, and then how to compute the coefficients. We wind up with a rimfire example and sum up. By the way, this is Jeffrey, our company mascot, and from time to time he weighs in. We needed a tool to calculate the coefficient of drag to support various projects. For example, 22 rimfire bullet profiling project, the subsonic centerfire project. We found the online tools were inconvenient, inflexible, and in some cases inaccurate. So for doing this work, the data formats and the formulas are a good fit for Excel, so that's the tool we went with there. And now we can compute values with both high accuracy and good precision. And using in combination with the on-target software, we can now correlate shot and group data with actually hits on target. Overview of the process, quite simple. We generally have a plan for what we're going to do and prepare for that. And then set up a weather meter, LabRadar, field notebooks, do our shooting, and then move the data into computer files. First step is to calculate environmental factors, and then move on to the calculation of drag coefficient and ballistic coefficients. We went with the WeatherFlow WEATHERmeter. This is an accurate miniature weather device. It connects up via Bluetooth to the smartphone or tablet and provides the wind speed direction as well as the data we need for work here, temperature, relative humidity, barometric pressure, and dew point. It'll work out to about 100 feet, so that's a good range for there. And the data is compatible with a variety of different ballistic calculators and other applications. You can either use this handheld or attach it by a 1/4-20 camera mount to a tripod. LabRadar is manufactured and designed by the same organization that makes the large-scaled units that you read about that being used by the ballisticians and bullet manufacturers. The difference is they've taken the antenna system, the data acquisition, the junction box, and the software, and have consolidated this all down into one simple, easy-to-use package. Sometimes you hear folks talk about this as an amateur or hobby unit. We disagree. This is a very precise unit. What's been done, it's been scaled down for personal use, giving ranges out to 100 plus meters, and it's a fully integrated solution. So it's very easy to set up and use, and nothing needs to go down range. It's Bluetooth enabled, not only the control of the unit, but the data acquisition back to the tablet or smartphone. So you have an additional larger display to work with. And then the real magic happens once you put in the SD card. This stores the summary and detailed trace data. This is a typical layout of how you would use the LabRadar at the range. As scientists and engineers, in addition to being shooters, we highly value our field notebook. We don't think about doing projects and experiments without taking notes. We find that missing data, that only happens in the field, will handicap your analysis later. So we strongly encourage folks to always take notes on what you're doing in the field. You're going to need SD cards. This is what's used by LabRadar to record detailed summary and trace data. This should be formatted to FAT32, and for Mac users, you format to MS-DOS. We've had good luck with a broad range of SD cards, except for some of the oldest, and we recommend you have a couple or several for backup. Here is the file structure you're going to see on the LabRadar SD card. There's the LBR directory, and underneath there are directories for each shot string you create. And then under each of these directories, you'll see a working file. This is no user information. This is used by the LabRadar system for communication between devices. And then you'll see a summary report in the Excel comment separated value file. Then under each of the strings, you'll also see directories for each of the individual shots that you take. So there's again in the Excel CSV file structure for each shot, there's detailed trace data for each shot in the group. We'll explain and get into this a lot more detail in just a moment. The first thing we want to do is calculate air density and the speed of sound. We do this by taking the data from the weather meter, temperature, barometric pressure, dew point, relative humidity, and use the WOBUS formula for calculating air density. There's a lot of detail in that formula, so somewhere along the line, someone named T-Trans came up with a simpler formula. This is one of those cases where online, these gave very different results. Once we put both of the formulas into the spreadsheet, ran the math, we find out they actually agree very well to 4 or 5 decimal places. So you could use either technique for calculating air density. From there, it's easy to get density altitude, which is going to be used by some of the ballistic calculators. We're not using it for the work here, but that's an easy number to get. But we do go on and use the Kramers formula for calculating the speed of sound. The Kramers formula for calculating the speed of sound is very detailed and takes in the environmental factors such as air density and barometric pressure. But the speed of sound is almost entirely dependent on temperature. So if you can live with probably less than 0.5% air, you can use this regression equation right here for computing the speed of sound. This is made up of using half a dozen so data points from the Kramers formula, and all the rest of the plots here are just our use of the equation. You'll notice small deviation up here predicted by the Kramers algorithm, but you see it's up there pretty high temperatures. So here's a quick, easy way to calculate the speed of sound. Here's an example of trace data that LabRadar records for each and every single shot. This is pretty amazing data. You'll see that the sampling rate here is from 1 to 2 milliseconds, and it's over the entire flight out to the level of sensitivity. This particular one is a 300 blackout. It's a 195 grain round nose flat point loaded with 9 grains of H110. And the regression is fit to this. What we're after here is a couple of things. One, we're interested in this equation, the slope and the intercept, and also we're interested in just how well that the regression, first order regression, fits the data, and here it does very well. We're just going to talk about 3 quick things here. One, you'll notice a gap right here. This is because LabRadar operates as a causal system. It doesn't see the future. Something's got to happen. Something's got to trigger it. In this case, it's the gunshot when the bullet leaves the barrel. So when that happens, there's a gap that happens from the time that goes off to the time the LabRadar can start to record the data. So whether you're using the acoustic trigger or the other triggering where the bullet enters the Doppler field, you'll see a small gap. So what the designers have done is they take these first few points, fit a regression to it, and go back and forecast what the muzzle velocity is. You'll notice when you fit a regression with this many degrees of freedom, it's not unusual to come up with a small difference here in the y-intercept. In this case, it's 344.1. So this is generally a very small error here. And in light of all the density of the data you've got through the flight of the bullet, that's a very small price to pay. 2 things also. One is that for high velocity bullets, a lot of times it's going to be 100 or 200 yards or so before they settle down. So it's possible you have some yaw and maybe some precession that is worked into the first 100, 150 yards that the LabRadar can record. So you want to keep that in mind. Always look at your data here and compare the data with things that are recorded in the larger Doppler systems, and just make sure you understand what that data looks like. The other thing is that folks are often surprised to find that the LabRadar will see the data on the other side of the target stand. So if you put a target stand at 50 yards, the LabRadar will see the bullet right straight through the target stand out to the limit of detection. Again, this isn't a problem. It's something to keep in mind, because with slow-moving, small caliber things like 22 rimfire, as that goes through the target and through the backer, that might upset that and introduce some yaw into that distance behind the target stand. Again, just something to be aware of and to keep an eye on as you look at this data. Ernst Mach was a 19th century Austrian physicist, actually a Renaissance man that made contributions to many areas of science. And in particular, he's known for his work with shock waves. Here's his seminal 1887 shadow graph of showing bow shock waves for a supersonic bullet. And in his honor, this relationship's been given his name. Velocity, in this case muzzle velocity, you get from LabRadar. And we showed earlier, just by measuring temperature, we can calculate speed of sound, and that gives us a Mach number. Mach is divided into regimes. Subsonic, here by definition is the speed of sound at sonic, but you'll also notice there's transonic, supersonic, and hypersonic. This is a very high level of importance for us in shooting, because unlike an aircraft that accelerates into the sound barrier, it creates the sonic crack. When we're shooting guns, they come out, particularly long-range, high-powered guns, they come out supersonic. So instead of positive acceleration going through the sound barrier with firearms, we actually start out supersonic and go through negative acceleration this way. So the transition from supersonic to transonic is of a high importance in long-range shooters. Down here, we go from transonic to subsonic, which is the case we look at for things like 22 rimfire. This is very important. We also will comment that going forward, I think you're going to see more of the literature values reported in Mach instead of velocities, because you take temperature out of the equation, you show it relative to the speed of sound, and that allows a lot better comparisons between ammo, bullets, charge loads, and things along this line. So keep an eye on this, and we're going to talk about this more in just a minute. Much of the work we do concerns the coefficient of drag, but we want to talk about the G models because this is where the ballistic coefficient comes in. The first is the G1, or the type 1, or the Ingalls shown here. All these measurements are in calipers. It's important to remember this isn't a real bullet. This was a construct that was put together and modeled so you can get this function of drag coefficient here against velocity. And in a moment, we're going to show how we tie the drag coefficient into the ballistic coefficient. Over the years, there's been several different G models developed. The most important are probably G1 and the newer G7. But there's also one called the RA4, which is specifically for 22 rimfire. Here's the diagram here, and again, all these measurements are in calipers. This is particularly important for us for the work we do for in rimfire work. You'll notice the function here that was developed is very different than the G1. But because the G1 is more established, a lot of times 22 rimfire ballistic coefficients are given relative to the G1. But for precise work, it's important to use the best drag function model as possible and in the case of 22 rimfire, that's the RA4. We'll show how this compares to the others in just a moment. We now have everything we need for calculating the coefficient of drag and the ballistic coefficients. We enter in bullet weight, bullet diameter, the air density and speed of sound we got earlier from reducing the environmental data. We have the velocity equation, both the slope and intercept from the LabRadar data for trace, and then we just need to enter in a range value for initial and final velocity. It's important to remember when selecting these values to make sure you're within the actual range of physical data you have. So you don't want to be picking values that are way outside the range from which you measured. But once that's done, the formulas go through and we get the Mach numbers for the final velocity, initial velocity, average velocity, and the coefficient of drag. All we have to do now to get ballistic coefficients, simply look at the drag function and look up the value for the closest one to our measured Mach number for both, in this case, the G1 and the R4A. Enter those in, and we get the ballistic coefficients directly. And as Jeffrey says, we are now good to go. Just a quick comment about this expression here. This is what's called the I, or the coefficient of form. No less of personages of people like Galileo, Newton, Bernoulli, Euler, and a host of others over the century have worked the problem of the flights of projectiles and bullets. But one of the things that we now have available, because of our ability to directly measure the coefficient of drag, a whole bunch of the modeling goes to the wayside. And to get this coefficient of form is simply taking our drag coefficient and ratioing that over those of the appropriate G model. This is really quite amazing and really points to the future and how this work will be done going forward. Let's bring this all together now with an example. We're going to use a 22 caliber rimfire. We're using a CZ455 varmint trader, 24-inch barrel, and the conventional 1:16 twist. The ammo is SK Standard Plus, 40 grain lead round nose. Here's bullet diameter. We track lot. And here's the reported muzzle velocity from the SK website. You'll see that they don't give a temperature, so we really don't have a chance to get the speed of sound. And then the ballistic coefficient relative to G1's given here is 0.172. And they're not stating whether they're using either the standard metro, the ICAO, standard atmospheric model. So this is kind of what we were talking about before. Without fully qualifying this measurement, we've lost the ability to do some meaningful comparisons. So going forward, we're going to shoot an indoor range, target stand at 50 yards, or bench rest. We're using bipod and rear sandbag, so the wind is out of the equation. Here's our atmospheric data as recorded at that time, and then also here's the speed of sound. So for analysis, here's the Mach number for our muzzle velocity measured at that time. And then we now have air density. And here's the ranges we selected for initial and final velocity. Here's the curve from the LabRadar trace data. So we're picking initial down here around 5 meters, and we're going out to about 75 meters here, which again is within the range of our actual measured value. We have the slope and intercept from the velocity equation here, and we can now directly calculate our coefficient of drag. We can go on and get the Mach numbers for initial, final, and average velocity. Here is the value of the drag coefficients from the table for G1 and RA4, and we directly get the ballistic coefficients for G1 and for RA4. You'll notice that this doesn't match up real well with what we see as the reported value. This is fairly typical because we've done a lot of detailed measurement here, and again, we're not even sure what the environmental factors were going in. But for us, the coefficient of drag is really the cornerstone measurement here, and this value actually correlates very well with data grabbed from work done by the Ballistics Research Lab in the early 90s. So it speaks to the power of fully qualifying your measurement and recording what you're doing, and you can get much higher quality data, which is really what we're after here. Okay, let's wrap up. LabRadar puts new capabilities in your hand like we've never had before. The system stays bench-side. You don't have to put anything down range. It's fast, intuitive setup, and it's very easy to use. It's powerful. You can look out well past 100 meters, particularly for larger projectiles. You can use it standalone, or else you could also tie it in by Bluetooth with the smartphone or tablet. And then once you plug in the SD card, you can see, as we've demonstrated, it opens up a whole new set of opportunities for data and analysis. We think people are going to start leveraging the power of analytics in the shooting sports even more. You pull in data from the weather meters, the LabRadar, use low-cost tools, Microsoft Excel, on-target software, TDS, and you can get a lot of powerful information about your loads and your shooting. And then you can even take this further. For instance, you could use the data from this to go on to calculate twist rate stability. Berger has a calculator online that you can use to help calculate the gyroscopic stability factor. It's very helpful for load development. And then also this data feeds in higher quality information into 4 degree of freedom, 6 degree of freedom, ballistic calculators. And then some groups such as Applied Ballistics and Hornaday, just to mention a couple, of now pervasively using the Doppler chronograph to actually come up with custom drag models and getting even more and more refined data for improving load development, shooting performance, and increasing your results on competitive shooting. We would like to thank Richard Moser and the folks out at TCK, who are the exclusive distributors of LabRadar, for their contribution to our presentation. And as you're thinking about subscribing, please look over these important notes and disclaimers. And thanks for watching. See you soon.